Testing. 1, 2, 3. 1, 2, 3. All right. I think my audio is good. Hopefully. All right. So this is going to be work, Calc 2, problem session 2. Ready? Guess I'll put it here. Calc 2. Let's see, here, Calc 2, problem session 2. No. It's applied. Okay. So let's go ahead and get started with the first problem, which I haven't actually looked at the particular first one because I think it's a pretty similar problem to what happened in last unit. But the idea is if you have two curves, y is equal to x and y is equal to square root of x. And they're going to meet, of course, at 1, 1. And we're kind of rotating them about, what is it? X is equal to 3, I think they say? Yeah, it's kind of a strange choice, but heck, why not? So if this is x is equal to 3, then 1, 3, you'd expect at 5, 1 to see kind of this pattern happening, right? And I'm just going to kind of interpolate this a little bit. Should I draw this, right? It's going to look kind of like a... I certainly do not have the right word for this. But it's going to kind of look like a... kind of a volcano, for lack of a better term. Yeah? Are you all happy calling this a volcano? Like, you're going to have some, like, volume around here, and it's going to like come around, but it's going to be hollow on the inside, right? And there's going to be sort of an open tip out here. Yeah, let's call this a volcano, shall we? And it's a little bit harder to integrate than maybe your average disk integration, because it's really more of a what do you call it? Each of these is sort of more of a washer, really. Right? But that's essentially the shape here. The idea is that it's really hard to it's really hard to draw. Yeah, so there's sort of like an inner circle that goes to the y is equal to x line. And, you know, for each height, there's sort of also an outer circle that goes to the outer one. Right? And then, of course, there's going to be a little height to this thing, like a little dy, I guess. But I'm not going to draw that part because it's already really visually cluttered. But the point is, we're going to add up, if we're being asked to find the volume, we're going to try to add up each one of these little washer things that have such and such area, right? The area it has is going to be the difference between the outer circle minus the inner circle, right? And the height is just going to be some little dy. Okay, maybe I will draw it. Right, so this little thing has a height here. So like you can kind of think it, I'm going to draw it sort of off to the side at a different scale here, but it's sort of like a wider, but very infinitesimally thin cylinder, subtracting out a slightly smaller cylinder. Yeah, that's basically what that is, right? They both have height dh and dh, but one has an outer radius, one has a larger radius than the other. And it's sort of like this thing is being subtracted out of this thing, sort of like hollowing out its center. That's essentially what a washer is, right? It's sort of like a circle subtracting out another circle. By the way, can I just do a quick mic check? I'm hoping to, explaining the problem, I'm just hoping that the audio is fine. Can you all hear me? Alrighty. So, very good. Loud and clear. So, all right. With this problem set up, let me see. I'm going to assume like maybe it's your first time or maybe you're still not so used to integrating washers. So let's just talk through it, right? The idea is we're hoping to, we're being asked to find the total volume, right? Yeah. We're being asked to find the total volume of the solid obtained around that region. So it's sort of like saying we're going to sum up all the little delta volumes, all the like tiny little infinitesimal volumes, right? Where a delta volume is the volume of one of these washers with a differential height dy. Sorry, I should be consistent. I should call it dy everywhere. dy and dy. All right. So delta volume is basically going to be, well, I'm just going to rewrite what delta, right? This is basically just the area of each one of these washers, which keep in mind does depend on the height y, right? Because the stuff towards the top is not going to be as big, right? The washers up here are not as big as the massive washers down there, just because this thing expands as you get to the bottom, because it's kind of like a volcano. Yeah. So let's call it a times y times, let's call it a tiny differential height. I'll use this triangle symbol to represent a differential height, delta y, right? And I'm going to turn the sums into integrals afterwards, but I just want you to sort of understand my thought process first. It's easier to explain with deltas. So, okay, I'll change this to a triangle instead. Right? So at this point, we basically just need to come up with an expression for this ay. And, well, we were sort of getting at this idea over here, but it's kind of like, if this, excuse me, if this radius right here is, sorry, let me just do a quick sanity. Yeah, we're rotating around x is equal to 2, right? So since we're like, maybe even before this, we're kind of, the natural thing to do is to kind of integrate with respect to y, right? Because as we integrate with respect to y, it's sort of like saying, like, I don't know how you put it. That's sort of what our axis of symmetry is, right? We're sort of going upward so that at each particular y value, you can kind of imagine the the washer centered around it. Whereas if you wanted to integrate with respect to x, that's like absolutely terrible, right? Because it's really, really hard to capture. If you don't want to integrate with respect to x, because it's really hard to imagine the volume associated with that little differential x, right? It's a lot easier to think about washers than it is whatever this like vertical abomination is. You know what I mean? So with that in mind, the justification here is we want the area in terms of y, but we know the equations where y is equal to x, y is equal to x, and y is equal to root x, right? But the point that I'm making here is the area for this thing is pi x squared, right? Or rather, it's like pi times x minus 3 squared. You see that? Because we're sort of centered about x is equal to 3. So the radius for the inner thing is just the distance from 3 to whatever that line is. And the radius for the other one is, you know, the exact same idea, x to the outer one. But the idea here is we basically just want to put this in terms of y instead. So this turns into, for this particular disk, if y is equal to root x, then x becomes equal to y squared minus 3 squared. You see that? It's just y squared is equal to root, if y is equal to root x for the wider disk, then y squared is just equal to x. You see? So like, let me remind you, a washer is basically just a disk minus a smaller disk. So this is basically the area in terms of x, and then this is the area in terms of y, which is what we want because we're kind of integrating with respect to y. So now we're going to do this exact same thing over here. This is area with respect to x is equal to pi times x minus 3 squared as well. It's just that for this one, x is equal to y, right? So a of y is going to be pretty much the exact same thing. Y minus 3 squared. That makes sense? Hope that makes sense. Yeah. Just doing a quick sanity check. So good so far? Um, yeah. If y is, yeah. Okay. So maybe I should have drawn it this way instead. Instead of drawing to the left-hand side, I should probably have just drawn to the right-hand side instead to show you the sort of correspondence between these lines right here and the radius that we're trying to capture. So anyways, that's basically our justification for these two expressions for area, right? So maybe let's call this A1 and A2y. One represents the outer disk and the other one represents the inner disk. And we just have to subtract them to get the overall area in terms of y. A1y minus A2y. So hopefully this is pretty reasonable step by step so far. A1y minus A2y. But at this point, we sort of just take all this, this is basically saying this is the area of each of these washers, and this is the height of each washer, right? That represents the little differential volume of each washer. And then when we take this into the limit, the sum becomes an integral as each of these delta y's become infinitesimally small and turn into dy's, right? So then this just becomes a1y minus a2y. And then the inner bounds of integration are just going to be from 0 to 1, I believe, right? Because, the down here it's 0, and up there y is equal to 1. Yeah. So, that's basically all there is to this problem, right? At this point, we have perfectly genuine expressions for a1 of y and a2 of y, right? This is going to multiply out to be some sort of fourth order in y, and this is going to come out to be some second order in y. But those are perfectly reasonable expressions to integrate. And I think that should be very, I hope it would be really straightforward from there. The bulk of this problem was just sort of going through the standard justification for why the disk method really even works in the first place. And I think that's really the meat here. Yeah? This probably isn't, I think I've explained it better in the past. But yeah, you could kind of think of this problem as, let me put it this way. You could have also thought of this problem as just being two totally separate integrals. A1y dy from 0 to 1 minus a2y dy from 0 to 1, right? And what this sort of physical meaning here is, this would have been the volume for the entire filled in volcano thing, right? Just totally solid, with the boundary condition being y is equal to root x. And then that would subtract out the area for the perfectly straight sides, right? That's sort of the smaller one, subtracting out this volume. So if you take this volume and subtract out this volume, you basically end up with the hollow volcano you get up there. Because that's sort of the same way to view, that's sort of a different way to view more or less the same math. But the idea is, because the integral is a linear operator, the difference of the integrals is equal to the integral of the difference, right? You can split it apart as you please, and you can think about either way. But at the end of the day, you're just going to be integrating some expressions that involve y here, and similarly there. And you just want to really make sure that you understand why you're integrating this, but from there on out, it should be one of the relatively straightforward integrals that you'll see. Yeah? Looks like a tasty flambe. I don't know what a flambe is. Hi. This thing is apparently called a frustrum. I looked that up the other day. But to me, I always thought that these things were like Jello cups. I don't know. Anyways, this is not a linguist class, but I think we should move on if hopefully that situation is comfortable now. So the next problem is one that kind of annoys me, because it takes a fair amount of justification to actually even come up with the expression for work in this problem. But I'm imagining that they never really explained it fully to you, and I'm kind of having to do a bit of a patchwork explanation that's good enough. Because, yeah. Anyways, let me explain as I go along. So the idea here is we're going to do something similar, but instead of calculating volume, right? We already are given, or we're not given the volume, but we're given a density of the water, rho, I believe, and we're asked to figure out how much work it takes to pump everything to the top. Right, and what that sort of means intuitively is you don't care about side-to-side motion, really. It's just saying for each one of these like infinitesimally thin sheets of water, how much work is it going to take to pump everything up to the top? And from there, right, you integrate everything, right? Because there's going to be one of these at every single layer here, and you just sort of add up all those pieces of work. So I'm going to be kind of a jerk for a moment, and I'm going to just write down the expression for work without really justifying it too much, right? Because, the general expression for work is force times, the miniature displacement, and this is a perfectly general expression for work where this force can be totally variable, like you could push fast and then slow, strong and then hard. And then, this integral accounts for everything. But it's really, really hard to think about a variable force in this problem. So we're going to kind of just mentally simplify things and treat this as a sort of constant force. And in particular, we're going to treat it as sort of like the force of gravity, mg, times whatever the change in height needs to be. Times, I'll call it change in height. So let me erase the integral for now, because it's really obnoxious how, they present this. Like, it took me a while to think of a fully rigorous justification for that expression, but the point being, I'm just going to sort of assert what our starting point is going to be, but basically, our little differential work, like for every single one of these slices right here, the differential work is basically going to be, what is it? It's going to be the little mass times gravity times the change in height, which is going to be big H minus little h. So if I'm defining little h to be sort of my independent variable, and little h is 0 down here, and up here, little h is equal to big H, right? So at this level right here, the height is h, and then the distance it has left to go is big H minus h, right? So I'm just asserting to you that this is basically what work looks like. For each of these individual layers, it's basically saying it's the differential mass of that layer times gravity times the distance it has to go upwards, all right? So I'm asking you to just sort of buy this for now. I can justify it in more detail later if you'd really want. But this is basically what the math class seems to be giving to you. Right? If you want to correspond it, this is kind of like your force, and this is kind of like your distance. That's kind of what that's saying. Right? But yeah, sorry, I find it really annoying just kind of having to make the assumption of constant force without proving why that's justified. But anyways, excuse me. At this point, we're basically wanting to rewrite this stuff in terms of other stuff that we have. So the way to rewrite this is basically to say, okay, if we're interested in finding an expression for our differential mass, we can rewrite this as rho times the differential, times the little delta volume of this thing, right? Because this thing has it's got some little delta H corresponding, and it's got some area, and overall it's got some delta volume, right? So that's rho delta V H minus H, which is equal to rho times area times delta H minus H. So good so far? Hopefully not too bad. But at this point, we just need to break down this expression for area a little bit. And it's going to look like our previous problem, but we basically need to put area in terms of h, because this is going to look like our integration variable, right? We're going to integrate with respect to this soon in a moment. So how do we put area in terms of h? Well, it's actually not too bad, right? We can kind of tell that, when h is equal to 0, r is equal to 0, and when h is equal to big H, little r is equal to big R, which happens to be equal to 1, right? But I'm doing this with general expressions rather than real numbers. So, but basically the point is right here that we have a directly linear equation, and it looks to me like r is just equal to h times r over h, I guess. Does that seem right? It really shouldn't be that crazy. It's just a linear expression, right? You can kind of just imagine this as h is equal to 0, r is equal to 0, and h is equal to big H, r is equal to big R. And you can just imagine taking 2 points and figuring out the line that connects them on a 2D plane. And it should be pretty easy to justify, right? If you wanted to be really explicit, you could, like, let's draw this out, right? So this is little r versus h, and you know that at 0, they're equal to, there's this point at 0, 0, and there's a point at big H, big R. So clearly the equation here connecting them is just a linear line with a slope r over h, right? That's what this is. Little r is equal to little h times r over h. And the reason I wanted to find this, of course, is because area, as we all know, area is equal to pi r squared, right? Area is equal to pi r squared, which lets us break down rho pi r squared delta h. And we can replace r with our expression for little h, right? Remember, little h is the variable, big R and big H are just constants. So at this point, we have a bunch of expressions, and we have this expression that's just all in terms of little h. I'll write it in just for posterity, but this turns into hr over h. I'll rewrite it as h minus h delta h, right? So, okay, wow, we went through all that work to figure out what the differential piece of work has got to be for each one of these disks. So now let's just add them all up, right? We just put a sort of sigma in front of each of these symbols to indicate that we're summing up across all the little heights. And then we're just taking the limit, right? We're taking the limit and letting this become, sorry, I missed a square here. H minus h times dh, right? That's just what this problem is. You can see why with these problems, the setup is the tricky part, right? You got to go through all this trouble to set up, figure out what that little differential element is. And after that, the integration is actually pretty straightforward, I would say. Darn it, why do I keep forgetting my squares today? And the limit for this thing, of course, I think I can leave this to yourself to figure, right? Just what's the limits for h for this integration? You know, what do you start at and what do you end at? Right, just, it's not a trick question, just plug it in. So r will always be 1 to 4 ratio of h. Yeah, I guess so. And let's keep in mind, you could have chosen a slightly different coordinate system if you wanted to. To me, it seemed like it would be simplest to define h is equal to 0 here and h is equal to big H here. But, like, you also could have defined, you know, h, I don't know, like some other wacky h, like h bar is equal to 0 here, and h bar is equal to minus h down here, right? Like, you could have chosen any coordinate system for this to work in. I just sort of eyeballed it and said, hey, this particular one with h equals 0, h equals big H seems the easiest. And just stuck with that. I guarantee you the math will work out all the same. Right? But, you know, keep in mind that if you're integrating in sort of a negative direction, sometimes you gotta have a negative sign pop out in the integral. Right? Because we're sort of integrating upwards. We're sort of integrating dh upwards. And I sort of implicitly, I should have said it before, but I'm taking upwards to be the positive direction for h. And negative to be the downwards. But anyways, I think I can leave this to you all, right? Just fill in the definite integrals and solve the rest of it. And the reason I went through that in so much painstaking detail is because I'm going to leave this part to you. I'll give you a little bit of intuition, right? But doing the little differential disk for the, version where it's upside down is not that different. It's just that you've got to set up a sort of different system now, right? Because if you're still defining h is equal to 0 and you're trying to figure out what your r is, yeah? Wait, did I draw this upside down or? No, damn it, I drew the exact same thing. Sorry. Brain fart. Oh my goodness. Wait, am I going all over the place? Sorry, what the hell? Sorry, I am just losing it today. This is what I want, right? For the one where it's upside down. All right, so if we're doing a differential disk, much is the same, but if you're choosing h to be equal to 0 and, this is going to be r, right? So h is equal to big H. The relationship between h and r is going to be different. And I think you just got to really figure that out for yourself. It's not hard, right? It really shouldn't be hard. So when h is equal to 0, r is equal to big R. When h is equal to big H, r is equal to 0. So just, this is just, it looks tricky, but this is just 8th grade math in disguise. It's, yeah, I'll let you figure out the relationship between h in terms of r. But what else is there to say? So this is still big H. And yeah, if you're letting little h be this part, and big H, then h minus h is still the height that it has to go upwards, right? So, a lot of this is going to look pretty much identical. It's just that the expression for area is going to be a little different. Yeah, that's basically it. The expression for area is going to be different, so this part's going to be different, but other than that, shouldn't be too bad, I hope. So, okay, that's the math part of this thing, but in terms of, like looking at a lesson and trying to figure out what's what, it asks you which one requires more work, or are they going to be the same, or, does that make sense? So just sort of looking at them, right, you can kind of see that work sort of means like how much energy you have to expend to lift all the stuff you want to lift. And just looking over here, there's a lot more water towards the top here that's already close to the destination, whereas down here, there's a lot of water that's really, really far down. Right? So kind of intuitively, this one's going to take more, it's going to take more to get this one up to where it needs to be because everything's really bottom heavy. You see what I'm saying? So I would not necessarily expect that your integrals would turn out to be exactly the same. And I think you can really just maybe sit down and think through the justification for why that is, why that seems reasonable physically and mathematically. Okay, so that's all I'll say there. Just think through it. All right, let's cruise through the rest of these problems. These were the sort of discussion heavy ones. All right, so for 3a, we're saying the work needed to free yourself from Earth is r to infinity, g times mass of the Earth times your mass over h squared dh. So I'm not gonna show how to do this because there's really not a lot to say, right? The g, the me, and the m are all just constants, so they can just pop right out. Right? They can just pop right out. So really you're just integrating 1 over h squared dh from r to infinity. So go ahead and do that. And you should be able to get what they think it's equal to. And okay, they include the definition of a proper integral, right? So the only thing to say there is that, okay, for proper integrals to like do it really painstakingly, it's sort of like saying, the integral of big H, or the limit as big H opposed to infinity of big H, right? Of, all this stuff down here, blah, blah, blah. And you just got to show this kind of carefully in your limit. When you finally have some expression, let's say you've integrated all this, right? And you get some expression in terms of, I think you're going to get some bunch of terms here like g ME, M, and it's all over like some terms in terms of little h, right? I won't tell you what it is exactly, but it's going to look like a bunch of stuff with little h, right? And you're evaluating these bounds from R to, well, you can't just technically plug in infinity right here. That's not very rigorous. You know, it's got to be the exact same thing. You got to plug in from R to big H, right? That's the proper way of doing it. But as you get more used to it, you can just sort of plug it in your head in certain situations. But to do it rigorously, it's supposed to be using a limit. Also, I think the notation is basically a straight line downwards. I always like using brackets for whatever reason. But this means plugging in H, and then plugging in, you know, subtracting out the thing, plugging it. Excuse me, it's basically saying plug in H and plug in R and subtract out the difference between those. Okay. So by the work energy principle, you're told that W is equal to 1/2 mv squared, where v is the velocity, and you're using that to show that v is equal to the square root of all that stuff. And there's really nothing to say there. Just take W is equal to 1/2 mv squared and set that equal to your answer from the last problem. And solve. I don't think there is anything more to say. Right? You'll get a little bit of cancellation. You notice that this expression here, the expression you're trying to achieve, 2gme over r, it does not depend on mass at all. It does not depend on mass. Or, I mean, sorry, it does not depend on your mass. It depends on the mass of the Earth, though. And you can kind of see that this r, as it gets smaller and smaller and smaller and smaller, you know, it's in the denominator, which means that this v is going to blow up, which means that the smaller the radius is, the more it shrinks, the closer it turns into a black hole, the faster you have to go to escape. And because there's a ceiling on the speed limit of the universe, namely the speed of light, you know, there's going to be some threshold at which v can no longer increase, and that same threshold is going to be the Schwarzschild radius. It's pretty cool. Yeah, so, you know, the part C, I think you should be able to figure out for yourself. It's basically just doing all that and just plugging it in. All right. So for the next part, I'm not going to use the exact points, but the idea is, okay, last time you learned what a Lorentz curve was, and this time we're going to do a bunch of approximations. So I think, you know, I'm just going to roughly draw the shape here, but it looks to me like X is increasing faster than Y for a little while, right? How do I express this? It kind of looks like 1, 2, 3, 4, 5, 6. Right, so it kind of looks concave upwards or something like that. And the idea here, like it's really very, like it's very really routine, right? You do a left endpoint approximation. So, you know, left endpoint approximation is when you just take the height of the left endpoint and take that to be the height of your rectangles. Your approximation rectangles. Oops. And, yeah, excuse me. Right, so you're going to get, I think it's just 5 rectangles. Right, that's going to be for left. And notice that this one is sort of 0 because the left endpoint is 0. But you're just going to go through and add up those areas, right? This is like the justification, you know, the justification between calculus, you know, is sort of intuitive, and it relies on essentially elementary school math, adding up the areas of rectangles. But then the next part asks you to do the same thing for right endpoint approximation. And, you know, it's just not that different. It's just saying, okay, instead of the left, use the right. Yeah? Just exact same idea. Just take whatever the width here and multiply it by the heights to get each of the individual areas and add them all up. Yeah. Keep in mind that left endpoint and right endpoint don't necessarily mean min and max. Like for this particular graph, left meant min and right meant max, but you could have imagined another graph going down in this direction that would have had the opposite relation where left was max, right was min. So, you know, don't get that confused. All right, last part tells you to do this as trapezoids. So how do I put it? You're basically going to just do some interpolations here and express these all as a bunch of trapezoids now instead of rectangles. And this approximation isn't perfect either, but it's a little bit better. you should be able to figure out what the areas of these are, right? It's just like, yeah, what the heck is the area of a trapezoid? It's just like area is equal to h times b1 plus b2 over 2, right? Hopefully I'm not crazy. Hopefully it looks something like that. But yeah, what else is there to say? Okay, now it asks if it's an under or overestimation, right? And it says that Lorentz curves are always concave upwards. Sorry, this is really hard to draw. Yeah, sorry. Drawing is not very good. Let me just focus on a little piece of it, okay? Let me just focus on a little piece that's maybe hopefully easier to see. But if this is between these two, right? Having it be concave upwards is going to be like that. And you can just kind of see it, right? You should just be able to visually see from this, convince yourself whether the curve is going to, sorry, the fact that it's concave means that it's got to be above or below. Just look at it visually and just draw it to yourself and convince yourself. But to say this in a little bit more mathematical detail. Oh, sorry. And from there, you should be able to figure out whether it over or underestimates. But to like describe this in a little bit more mathematical detail, right? This has to do with a second derivative. What do we say? It's sort of like saying, if the fact that the concave upwards means that the second derivative is positive, sort of means that, like, if you think about like how fast it's rising as kind of like the acceleration, it's basically saying, well, at first it's not going upwards very fast because it hasn't accelerated for very long yet, but after a bunch of time it's going to accelerate, you know, even faster to catch up, right? That's sort of what concave upwards means. Or rather, like, let's say it's accelerating constantly, right? It means that it's not going very fast at first, right? It's going to fall behind this other curve, but it's going to pick up more and more speed because of the acceleration over time, and that's going to allow it to catch up. That's what that means. So that, let me put it this way. If this curve kept going, it would overtake this line at the point that they meet, right? But because of the way the trapezoidal approximation works, you get replaced by a new linearization, by a new line. So you don't get to see the overtaking. All right, anyways, we're getting to the end here. The next couple of problems start to become pretty just computational, I think. Cosine cubed theta plus sine 2 theta. Sine 2 theta minus 3 cos theta over sine cubed plus 3 cosine squared plus 2 sine theta minus 3 cosine cubed theta plus sine 2 theta minus 3 cosine theta, right? They suggest you to use a little bit of u substitution where u is equal to sine theta. So therefore du is equal to cosine theta d theta. And I'm just going to quickly show the substitution just a tiny bit to sort of get you the idea, right? But rest assured that things are going to work out really nicely. So up the top here, yeah, this just becomes, let's take a look. Cosine, I'm going to write it this way, cosine squared of theta times cosine theta plus, now the double angle identity is just sine 2 theta is equal to 2 sine theta cos theta. Yes? So that's the double angle identity. Minus 3 cos theta. That's going to get all divided by sine cubed plus, now I'm going to use another sine identity. This turns into 1 minus sine squared theta plus 2 sine theta minus 3. So that's going to be d theta. And you notice that there's a factor of cosine in each of these terms. So that turns into, let me write it, cosine theta, d theta. And now this little cosine squared theta can also be represented with an identity. It's 1 minus sine squared theta. We used it just earlier, but now we're going to use it again. So this is plus 2 sine theta minus 3. So that's the numerator. This is just a tiny bit of algebra, right? I'm factoring out the cosine theta, and I'm doing the double angle, or not the double angle, but the sine squared, cosine squared identity. And then down here we have sine cubed. The plus 3 and the minus 3 cancel out, so we get a minus 3 sine squared plus 2 sine theta. So you notice that you can also get a theta to factor out down here, too. But yeah, things should start looking really, really nice. Yes? So this part, cosine theta d theta, oh, why did I write that twice? Becomes your du. Yes? And then at this point, you can just plug in u everywhere where you see a sine. And things should work out really, really nice. You should be able to see some cancellation, for one. And yeah, I just say work through it. And yeah, it's definitely going to look pretty nice. You might have to, I'm not entirely sure, but I think you might have to do a partial fraction decomposition near the end. I didn't work this out all the way myself, but it just looks like it turns out fairly clean. Yeah, partial fraction decomposition is not the worst thing in the world. I would suggest you just quickly Google that yourself, because I don't think there's any point to me rehashing something that there's, a billion good videos for. But that's basically the idea. You just break things down, and it just was contrived to all work out really nicely. All right, I think we're getting to the end here. Gosh, just 2 more. Yeah, so for this one, a probability density is, for a function to be called a probability density, it needs to satisfy 2 things. All the probabilities densities need to be non-negative, right? That's what they mean by this first condition. And then integrating it from all on the entire domain, it's got to add up to 1, right? Because just intuitively, the probability, the sum of all possible events has got to be 1, right? Like you flip a coin, it'll be heads or tails, 50% each. They've got to add up to 100%, right? Otherwise, it's just nonsense. Or like, gosh, what's a good, like horse racing, right? Like, let's say the first horse has a 40% chance of winning. The second horse has like 20%, then 10%, then like 10%. Like, it's got to add up to 100%, right? That's just our definition of probability. It doesn't make sense unless it's out of 100%. And that's what that one means. It means 100%, right? But, okay. They're just asking you to do a little bit of integration, and I don't know that there's necessarily anything for me to... I don't know that there's a lot I can shed light on here other than just saying to go ahead and do these integrals. So you're integrating... Okay, so maybe I'll give you like a brief talk through of what, pitfalls you need to avoid. But they're telling you that the integral of f of x on 0 to e is 1 over x, and it's 0 otherwise. So what this looks like is basically... it's 0 out here, and then it suddenly has like this vertical asymptote and coming down like that. Yes? So, okay, we can verify the first condition is true. That's much as obvious. I don't feel bad about saying that, right? Everything is obviously non-negative. There's no values down here. It's obviously non-negative. But the second part means that you actually have to integrate it. And even though this is a piecewise function, this goes from 0 to e, and then it goes back to 0, right? So don't get confused. Don't get too confused about integrating from negative infinity to infinity, right? Because I'm trying to imagine what a first-time student might be confused by, and they see that, oh, this is only from 0 to e, so how do I integrate it from negative infinity to infinity? Well, the integrals for these parts and this part is just 0, so don't even worry about it, right? It's sort of like saying the integral from negative infinity to 0 plus the integral of from 0 to e plus the integral of e to infinity. The stuff here is just 0. And then the stuff over here is 1 over x. So I'm saying that this is the only integral you need to care about. So go ahead and integrate that and see if you're basically asked, do you get 1? Right? If you get less than 1, that's bad. That's a fail. If you get more than 1, that's bad. That's a fail. And if it diverges, right, if it goes off to infinity or minus infinity, that's also a failing condition. So just do that for all three problems. I think you're just being asked here to test your integration techniques. And yeah, that's basically all there is to say. None of the integrals I think are particularly complicated. They're all pretty, I think they're all pretty elementary. Just remember to use chain rule where appropriate. And remember all your other integration rules too. So, okay. Now they say that we can, for part B, they say, okay, that's a probability density function. Now we can find the expectation value, expected value. Okay, I can talk a little bit about this. Again, I'm not going to do the integral out for you, but whereas before you had to integrate 1 over x dx, now you just have to multiply the integrand by another x. And this may seem really mysterious the first time you're doing it, but I assure you that it's really not. Like, how do I put it? An expectation value is really just your average, like your average winnings in a bet, or your average value on a bet. So you could possibly consider maybe the 4 horses I was talking about, where maybe horse A has a 0.4% chance of winning. So let's call that your probability. And then let's say your dollar amount payout is 1, because, you know, not very high because it's the best horse. And then, okay, let's say horse B is 0.2, horse C is 0.1, and horse D is 0.1. So, wow, I did not add that up right. Okay, let's say that there's also an E and an F with 0.1. So let's say that your winnings for this horse is $1. Over here, it's sort of like maybe $2. And over here, it's maybe $4 for each of these, because they're a little bit less likely. But the idea behind an expectation value is basically saying, so, you know, if probability was your equivalent of f of x, and the money was equivalent to, I guess, x, your payout, the expectation value is basically just the weighted sum of these. So it's like 0.4 times 1 plus 0.2 times 2 plus 0.1 times 4 plus the exact same thing like 3 more times, right? It's basically just saying what's your average winnings if this was like a betting situation. Only instead of the finite case where there's 6 possibilities, now there's an infinite number of possibilities. You know, there's a possibility for each value of x in the number line. And it's just sort of like smoothing that out from a discrete math into continuous math. You see what I mean? Hopefully that's not too crazy a concept. Hopefully that makes sense. But yeah, go ahead and do that, and then just choose whichever one seems the easiest to integrate for you. Hopefully it's not too crazy. All right, last problem. Exciting. I was really expecting to get this done a lot faster, so I ended up talking a lot more. All right, so you're basically told y is equal to e to the minus x with x greater than or equal to 1. And you are being asked that someone is rotating this about the x-axis. And they're, okay, you got to make a sketch of it, sure. But the idea is it goes sort of off to infinity, right? And off the top of your head, it's not so obvious whether or not this is going to be an infinite volume, or if it's going to somehow be finite. And yeah, it's a little tricky. It is a little tricky. The reason it's not so obvious is because x grows x goes off to infinity, right? But y is equal to e to the minus x gets small really, really, really fast. So it's not clear whether or not the fact that x is infinite wins out, or if y gets small enough for the areas of these disks to get small enough as you go forwards for the volume to end up being finite. So to figure out, you just have to go ahead and integrate. But the concept is very similar to what we had earlier, right? We basically just wanted to add up the little differential volumes, and each one of these cylinders, well, they're kind of rotated sideways now, but they each have an area, and they each have a little height delta x, right? A differential height. So now we just need to express the area in terms of pi y squared delta x. And now you just need to express y in terms of x. You just got to replace it, right? And then after that, you're going to turn that into an integral. So yeah, that's basically all there is to it. Just go ahead and, solve that through, plug in the bounds, or take the limit where appropriate, and see if it's finite or if it's infinite. And that corresponds to whatever your volume is. So go ahead and think that through, and hopefully it should all work out well. Any last questions? Alrighty. I think that'll do for today.